Hi and welcome everyone. In this video, we're going to go over linear transformation and matrices, see how they're related, and I'm going to do a couple of examples so you can see how matrix addition, subtraction, multiplication, and inverses work when you have the transformation and then you change that to matrices. As you remember, whenever you have a linear transformation, you always have a matrix involved with that. So let's go over matrix addition and subtraction. Please watch my last videos on those. So if you have addition or subtraction, if we write the matrices in compact form, that's an n by n matrix and that's an n by n matrix. They have to be, because if you add and subtract, they have to have the same size. So when you add, you just add or subtract the corresponding entries. I being a number between 1 and m, these are the number of rows, and j being a number between 1 and n number of columns. Now let's do an example, see how that works. If you have a transformation from R3 to R2 and another one from R3, R2, and they have to be the same. So if you write the transformations are t of x, y, z is 3x minus 2y plus 5z and 2x plus 4y minus 3z. So we are going from R3 to R2. So if you have another transformation T2 the same way, the matrix for T1, again, it's you can write x, write the components of x is 3, 2, the components of, not the components, coefficients of y is negative 2, and 4, and so on. So you can write the same matrix, the matrix also for T2, and that's what you get. Again, for X, you have 4, 1. I'm sure you know that by now. Watch my previous videos. So we have the transformation and their matrices. Now, if you add these two transformations, so you can just take that plus that. So the first component of the vector and the second component. And if you do that, so I also wrote it for you. So 3x minus 2y plus 5z plus 4x plus 7y minus 2z. And you get that. The second component, you get that expression. The matrix for this, again, is going to be for x, you're going to have 7, 3. 7, 3, for y is 5, 3, and for z is 3, 1. Very straightforward. And if you go back and add the matrices of the transformation separately, which we had it here, that matrix plus that matrix, you get this matrix, and again, you add the corresponding entries. So if you do that, then you are going to end up with the same matrix. So you can have the matrices and add the matrices, or you can add the transformation, then find the matrix. You are going to get the same answer. Now let's see how this works for matrix multiplication. So again, to start this, first let's review the composition of functions. From pre-calculus or calculus, we know when we have f rho g, that's f of g of x. And again, that's, you read that, that's rho, the Greek letter. So for example, if you have a function 2x plus 1 and g of x is 3x minus 2, f rho g or fog is f of g of x. So basically, you go to your f of x, and wherever you have x, you substitute that by g of x, and you simplify, that's what you get. See how that works for transformations. If you have a first transformation, you go from Rn to Rk, and the second one, you go from Rk to Rm, and make sure these are the same. Now T1 rho T2 is going to go from Rn to Rm, from here to here. So let's look at it another way. So if you have a vector in Rn, T1 of u is going to give you a vector in Rk, and T2 of v is going to give you a vector w in Rm. T1 rho T1 of u is the same as T1 of u and that's, we know that's V, so it's T1 of V, and that's going to give you W. Let's look at this example. We have a transformation from R3 to R2 and another one from R2 to R3. Make sure these are the same. The codomain of the first one has to be the same as the domain of the second one for composition. So these are our transformations. T1 of x, y, z is x minus y plus 2z, 3x plus y minus z, and T1 of uv is u plus 2v, and the second component 5u minus v, 3u, and u plus v, and it's in R4. We clearly see that. So now, if we want to write T2 rho T1 of XYZ, that's T2 of T1 of XYZ. So basically is T2 of x minus y plus 2z of that, and that's going to be our u, and of that, which is going to be RV. Basically, you go to T2, wherever you see u, you substitute that by x minus y plus 2z, and wherever you see v, you substitute that by 3x plus y minus z. And I wrote that here for you. So it's u plus 2v, so it's going to be that plus 2 times v, and so on for each one of them. Please double check that. And finally, you can simplify, and you have, let's see how many components, 1, 2, 3, and 4. So if you write the matrix of that T1, T2 row T1, again, for X, you have 7, 2, 3, and 4. It's right here, same thing for Y and Z. So this is what you get. Now the separate matrices for T2, if you write the matrix, write U and V, and you put the coefficients. For T1, it's X, Y, Z, and you put the coefficients. This is a 4×2 matrix, and that's a 2×3 matrix. And again, if you write it, it's 4×2 and 2×3. Now let's multiply those matrices. So if we take T2 times T1 and we multiply, and I'm sure you know matrix multiplication already, and this is 4×2, and that's 2×3, and if you multiply, you should get a 4×3 matrix, which we do. Let me just do the first entry. So 1 times 1 plus 2 times 3 is 7, and you please watch the video on matrix multiplication. I already have that video up, so that's what you get. And if you compare that, that's the same matrix as the composition. So composition of linear transformation can be performed by matrix multiplication. So let's take a look at the inverses. So if you go from R2 to R2, and that's a linear operator, and this is our transformation. The matrix for that is 3, 7, 2, 6, and we know clearly where this is X, this is Y. If you find the inverse of T, then you get that matrix. Now we have, if you write the composition for the inverse, so again, for x's, you have 3/2x and -1/2 x. You're kind of going backwards. If you do T inverse rho T xy, so basically you're going to do T inverse of that, the composition of these two matrices. And if you write them, you just substitute. You can go to the inverse, and then instead of x, you can substitute that. Instead of y, you can substitute that. If you want to perform the composition, and if you do that, you get xy. And what is xy is just the same thing as, so you can write this as x0 plus 0 y, which is the identity matrix. And if you perform, we know that T times T inverse is going to give you the identity matrix. So these were simple examples to explain how you can relate transformations or operations with transformations with operations with matrices. Thank you for watching, and I'll see you in my next video. Have a good one.